Alright, this is my audience of one for COM 101. I'm Alex Hettwer, and this is speech number 2, the informative speech. When we first learned how to calculate volume, we learned that cubed units were the units to use, and that's really good because they're standardized and everyone knows what they mean. But then we got into curved spaces, and we weren't quite sure how to figure that out. Our teachers and our textbooks bailed us out by giving us a lot of nice formulas to use, like for a cone or for a sphere. But I was always thinking, where do these formulas come from? And I ended up pursuing a career in math in my education. Today I'm going to be demonstrating how you actually find the formula to solve for the volume of a cone. During this, I'm going to be covering interesting properties of a cone that allow us to do this more easily, the math behind it, mainly integrals, and how you combine both of them to actually get an answer that means something. I'm going to begin with the properties of a cone. In Rogowski's book, Calculus Early Transcendentals, the 2015 edition, he mentions that the cross-sections are very important in calculating cones. And what I'm going to focus on is cones with cross-sections that are circular. Here's a diagram of one, and the basic method of doing this is you chop up the cone into really small pieces, and you just add up all the cylinders that you get. When you flip it on its side, you find that the cone forms a triangle when you bisect it. And this is really, really helpful when you're finding the area with an integral. This is helpful especially because right triangles have a very special property that when you cut them into another right triangle, they form a similar triangle, and it lets us write something like this. This is really good because we need the area of a circle because we're going to be adding up a lot of areas of cylinders, and we can't use that in the integral. We need the change in height, and this gives us a formula to use the height in a way that's useful to us. And now that the properties are done, those are the main properties that we're going to use. I'm going to touch on the actual math that we need to use to solve this. My professor, Dr. Stryker, in a review lecture in 2018, I thought she defined an integral really well in saying it's just an infinite adding machine. It's nothing to be afraid of. Today we're going to be adding disks, and that's how we're going to find the actual volume of the cone. After we set it up, as shown here, there are only actually 2 rules to follow that we need to use to find the formula of the volume. The integral is basically, this tells you where you're integrating, this tells you what you're integrating, and this tells you what you need the variable to be in terms of. After you get that down, the first rule, also in Rogowski's 2015 Calc Early Transcendentals, is the power rule. This actually solves polynomial integrals. What it says is, when you have a polynomial, all you have to do is raise the power by 1 and divide it by the value of that new power, and then you've solved the indefinite integral. But we're not interested in that. We want actual numbers, an actual formula that we can use. So we need the fundamental theorem of calculus to turn it into a real number. What the fundamental theorem of calculus says is, after you get the indefinite integral found out, all you need is the bounds, and you take the upper bounds, subtract the lower bounds, and you have your answer. So, we're good on the math. That is actually all the math we need. And now we're gonna smash them both together, and we're gonna actually solve for the formula. Exactly how the integral should look, just like we set it up before, but now we plugged in values. This is the area of the circle, since we're going to be adding up a bunch of them. This is the width, and in an integral it actually approaches 0, so it's almost like you're adding up 2-dimensional figures to get a 3-dimensional volume. And then this is what we're going to be integrating on. It goes from 0 to the maximum height because we want the full cone. We don't want part of it. After that, we're going to replace it with the ratio we had before, because we don't want the radius, we want the height, because that is what we're going to be integrating with. So now that we have that, all it takes is a little bit of algebra, and we're ready to use the power rule. After we get done with the power rule, this is a solved indefinite integral, but we just need one more step to actually get the formula that we all know and love. After you solve for the indefinite integral by just plugging 0 and h into the respective parts of the fundamental theorem of calculus, the second part of it disappears because you're just plugging in 0, and you get the formula that we're all used to. And I really, really love this formula because it means I don't have to do all of that math every single time I want to find the volume of a cone. So, in closing, today I demonstrated how to find the formula for a volume of a cone. In doing this, I elaborated on the properties of a cone that allow us to do this, the math in calculus that makes it much easier and much more precise, and how to smash them both together in order to actually get an answer that makes sense. Unix cubed used to be a problem when we were dealing with curved surfaces, but with the help of calc, it works just fine, and we can get exact answers. Right, and then I need to get you on camera one more time. Alrighty.